There is a moment, a single, unrepeatable moment that will occur sometime in 2026, high above the Pacific Ocean at a speed no human being has survived in over 50 years. 4 astronauts, 1 capsule, and 20 minutes that will determine whether the most ambitious crewed mission since Apollo comes home safely or becomes the most catastrophic loss in the history of human spaceflight. This is not a hypothetical. This is not a simulation. This is the physics of what happens when you take a spacecraft traveling at nearly 40,000 kilometers per hour and ask the atmosphere of Earth to slow it down using nothing but friction, geometry, and a heat shield that was never tested at this exact speed with humans inside. Artemis 2 is not just NASA's return to deep space. It is a confrontation with one of the most brutal, unforgiving, and poorly understood environments in all of aerospace engineering. And the most dangerous part of the entire mission, more dangerous than launch, more dangerous than the lunar flyby, more dangerous than 4 human beings floating 250,000 miles from the nearest hospital, is the last 20 minutes, the re-entry. And once those 20 minutes begin, there is absolutely nothing anyone on Earth can do to help them. Let that sit for a moment. From the instant the Orion capsule touches the upper layers of the atmosphere, all communication with the crew goes dark. Mission control in Houston cannot talk to them. The astronauts cannot talk to mission control. The capsule is surrounded by a sheath of superheated plasma so electrically charged, so intensely ionized, that radio waves cannot penetrate it in either direction. The crew is alone, encased in fire, moving faster than a bullet from the most powerful rifle ever manufactured, and they have to get the angle exactly right, because if they come in too steep, they burn alive. If they come in too shallow, they bounce off the atmosphere like a stone skipping across water, back out into space with no way home. This is the countdown that nobody talks about when they talk about Artemis. Everyone focuses on the rocket, the launch, the mission, the moonshot. But the engineers who have spent years working on the Orion capsule's re-entry systems will tell you, quietly, in the language that aerospace people use when they want to be honest without causing panic, that re-entry from a lunar return trajectory is the single most demanding thermal and aerodynamic event in crewed spaceflight. More demanding than anything the space shuttle ever faced, more demanding than Soyuz, more demanding in specific and measurable ways than even the Apollo missions that did this exact thing half a century ago, because the Artemis 2 crew won't just be coming home from space, they'll be coming home from the moon, and that changes everything. To understand why 20 minutes could end everything, you have to understand what those 20 minutes actually are. You have to understand what the Orion capsule is flying through, what it's made of, why the angle matters down to fractions of a degree, and why, despite all of our technology, all of our computing power, all of our accumulated knowledge from 65 years of human spaceflight, we have not done this with a crew in this precise configuration since December of 1972. That was the last time human beings returned from the moon. That was the last time a crewed vehicle entered Earth's atmosphere at lunar return velocity. That was 53 years ago. And when Artemis 2 comes home, it will be doing something that even the Apollo missions never attempted. Something called a skip re-entry. A maneuver so precise, so geometrically demanding, and so physically violent that it has never once been performed with human beings inside the vehicle. The only data we have comes from one uncrewed test flight. One. And that test flight Artemis 1, which flew in late 2022, came back with damage to the heat shield that engineers did not fully predict and still do not completely understand. We are going to count down through every phase of those 20 minutes. We are going to walk through what happens at the moment the capsule first kisses the atmosphere, through the blackout, through the skip, through the second entry, through the deployment of the parachutes, and finally through splashdown. We are going to look at every failure point, every margin, every place where the difference between survival and catastrophe is measured in degrees, in centimeters, in milliseconds. But first, we need to go back to understand why coming home from the moon is so fundamentally different from coming home from the International Space Station, because most people, when they imagine a spacecraft coming home, imagine the space shuttle gliding down to a runway or a Soyuz capsule hanging under orange parachutes over the Kazakh steppe. Graceful, controlled, almost routine. Lunar return is none of those things. The International Space Station orbits Earth at approximately 400 kilometers above the surface. The speed required to maintain that orbit, the speed at which the ISS and any capsule returning from it travels, is roughly 7.7 kilometers per second. That is fast. That is genuinely, almost incomprehensibly fast. It is 27,700 kilometers per hour. It is fast enough that a vehicle at that speed, coming into the atmosphere incorrectly, would generate temperatures capable of melting steel, and yet 7.7 kilometers per second is slow compared to what Artemis 2 will be doing. When a spacecraft returns from the moon, it has been falling toward Earth from a distance of roughly 400,000 kilometers. The moon's gravity launched it away. Earth's gravity is pulling it back. And by the time it reaches the upper atmosphere, the invisible boundary called the Kármán line, sitting about 100 kilometers above the surface, it is not traveling at 7.7 kilometers per second. It is traveling at approximately 11 kilometers per second. That is 40,000 kilometers per hour. That extra 3.3 kilometers per second, the difference between ISS return velocity and lunar return velocity, does not create a proportionally larger problem. It creates an exponentially larger one. The kinetic energy of a moving object scales with the square of its velocity, which means that the Orion capsule returning from the moon carries not just a little more energy than a capsule returning from the ISS. It carries approximately twice the kinetic energy, and all of that energy has to go somewhere. It cannot be stored. It cannot be redirected. It has to be shed, converted, dispersed. And the only tool available for that job is the atmosphere itself. Atmospheric reentry is, at its core, a controlled crash into air. At the speeds involved in lunar return, air does not behave like air. It does not flow around the capsule the way air flows around a car on a highway or even around a fighter jet, breaking the sound barrier. At 11 kilometers per second, the air molecules in front of the capsule cannot get out of the way fast enough. The information that something is coming, which travels at the speed of sound, roughly 340 meters per second, moves 22 times slower than the capsule itself. The air has no warning. It is simply compressed, instantly and violently, into a layer of superheated plasma in front of the heat shield. That plasma, that sheath of electrically charged, disassociated gas, reaches temperatures of approximately 2,760 degrees Celsius. That is hotter than the surface of the sun's photosphere at its coolest regions. It is hot enough to vaporize iron, hot enough to turn most metals used in aerospace engineering into vapor in seconds. The heat shield on the Orion capsule is made of a material called AV coat. It is an ablative heat shield, which means it does not simply resist the heat. It absorbs it and then burns away, carrying the thermal energy with it as it vaporizes. The outer layers of the heat shield are designed to be sacrificed. They char, they ablate, they are consumed. And in being consumed, they carry the heat away from the capsule and the crew inside. This is a technology that has existed since the early days of the space program. The Apollo capsules used ablative heat shields. So do modern Crew Dragon capsules returning from the ISS. The concept is not new, but the Artemis 2 heat shield is the largest ablative heat shield ever flown on a crewed spacecraft. The Orion capsule has a base diameter of 5 meters. For comparison, the Apollo command module was just under 4 meters. The additional size is necessary because Artemis carries 4 crew members with their equipment and suits, and because the mission profile demands it. But a larger heat shield does not simply mean more of the same material arranged over a bigger area. It means new engineering challenges, new structural dynamics, new questions about how the ablative material behaves uniformly or fails to behave uniformly under extreme thermal stress. And this is where the story of the Artemis 1 heat shield becomes critical to understanding the danger that Artemis 2 faces. In November and December of 2022, NASA flew Artemis 1. It was an uncrewed test flight of the complete Space Launch System and Orion capsule stack. The mission went to the Moon, entered lunar orbit, and came home. It was, by NASA's official assessment, a successful mission. It demonstrated that the SLS could launch, that Orion could survive the lunar environment, and that the heat shield could handle lunar return reentry. Except when engineers examined the Artemis 1 heat shield after splashdown, they found something unexpected. The ablative material had not worn away uniformly. Chunks of the charred AV coat material, pieces larger than engineers had predicted, had broken off during re-entry, not in a way that compromised the mission. The capsule survived, but in a way that raised questions. Questions that, when they were asked loudly enough, became serious enough that NASA spent over a year conducting an investigation into what had happened and why. The technical term for what they found is spallation. It is a process by which the char layer on an ablative heat shield breaks apart under mechanical stress, the combination of intense heat and intense aerodynamic pressure, creating conditions where the charred outer layer fractures and detaches in pieces rather than vaporizing smoothly. The pieces that detach expose fresh AV coat beneath them to the full heat of the plasma. That fresh AV coat then ablates more rapidly than planned, which means the heat shield is consumed faster in those areas, which means the margin between survival and breakthrough, the margin between the heat shield doing its job and the heat finding a path through to the capsule structure, is reduced. NASA's investigation concluded that the spallation seen on Artemis 1 was within acceptable limits for that uncrewed mission. The capsule survived with margin remaining. But the investigation also concluded that the spallation was driven in part by a specific phase of the Orion reentry profile, a phase that is unique to lunar return, and that has no equivalent in the re-entry profiles used for ISS return missions. That phase is the skip, and the skip is the most extraordinary, most counterintuitive, and most dangerous maneuver in the entire 20-minute sequence. Here is the problem that the skip re-entry was designed to solve. When a spacecraft returns from the Moon at 11 kilometers per second and enters the Earth's atmosphere on a standard ballistic trajectory, the kind of trajectory used by the Apollo capsules, the deceleration forces experienced by the crew are extreme. During Apollo re-entries, crews experienced peak G-forces of around 6 to 7 G. 6 to 7 times the force of gravity, pressing their bodies into their seats with the weight of 6 or 7 times their own mass for several minutes. This is survivable. The Apollo astronauts survived it, but it is at the outer edge of what a human being can tolerate, particularly after days in microgravity, and particularly for crew members who may not be in perfect physical condition. The Artemis program has made a commitment, driven by NASA's goals of inclusivity and the desire to fly a more diverse range of crew members, including people who may not have the extreme physiological conditioning of military test pilots, to limit the peak G-load during re-entry to approximately 4 G, 4 times the force of gravity. This is still punishing. It is still far beyond anything most human beings will ever experience, but it is within the tolerance range of a broader range of bodies. The problem is that you cannot slow down from 11 kilometers per second to 0 using only 4 G of deceleration if you fly a standard ballistic trajectory. The physics do not work out. You either accept higher G-forces or you find a way to extend the deceleration over a longer period and a longer distance. The skip re-entry is the solution. Instead of plunging directly into the atmosphere and riding out a steep, violent deceleration, the Orion capsule is guided into the atmosphere at a shallow angle. It dips in. The atmosphere compresses in front of it, the heat shield does its work, the capsule slows down, and then, at a precisely calculated moment, the capsule uses the lift generated by its own shape and orientation to bounce back up, out of the atmosphere, back into near vacuum, like a stone skipping across the surface of a lake. For a few moments, the crew is no longer in the atmosphere. They are above it. The plasma sheath around the capsule cools, the thermal load on the heat shield drops, the deceleration pauses, and then the capsule arcs back down. For a second entry, slower now, having shed a significant fraction of its kinetic energy during the first pass. This second entry is slower, gentler, more controlled. The G-forces during the second pass are lower. The peak total G-load across both passes stays within that target of 4 G. It is an elegant solution to an enormous engineering problem. It is also, in the words of several aerospace engineers who have spoken publicly about the Artemis program, one of the most difficult guidance and control challenges in the history of crewed spaceflight. Because the skip is not a passive maneuver, the capsule does not simply bounce. It is actively controlled throughout the first pass, the skip, and the second entry by a guidance computer making thousands of decisions per second, adjusting the capsule's orientation using small thrusters, managing the lift vector, calculating and recalculating the trajectory in real time based on the actual conditions it encounters, atmospheric density, capsule mass, thermal loads, all of which vary from the pre-mission predictions in ways that are impossible to model perfectly in advance. The guidance computer has to get it right every time, with no margin for a second attempt, and it has to do this while the capsule is surrounded by plasma that has severed all communication with the ground. The crew cannot be told what to do, mission control cannot intervene, the computer cannot phone home for instructions. Whatever happens inside those 20 minutes, the 4 people in the capsule and the software guiding them are entirely on their own. This is what the countdown to those 20 minutes looks like from the outside. This is what makes every engineer who has worked on the Orion re-entry system look slightly uncomfortable when they are asked, in public, whether they are confident in the heat shield. They say yes. Of course they say yes. They have run the simulations. They have analyzed the Artemis 1 data. They have made modifications to the ablative material layup on the Artemis 2 heat shield based on what they learned. They are confident. But confidence in aerospace is not certainty. And the gap between confidence and certainty is exactly the space where disasters live. In the coming parts of this video, we are going to walk through those 20 minutes in real time, phase by phase. We are going to look at what the crew experiences during the atmospheric interface, the moment the plasma begins. We are going to examine the blackout, what it means, how long it lasts, and what it felt like for mission control during Apollo when communication disappeared. We are going to go through the skip itself, the physics, the guidance, the failure modes. We are going to examine what happens to the heat shield across both atmospheric passes, what the temperature timeline looks like, and what the structural margins are between survival and catastrophe. We are going to look at the parachute sequence, a system with its own critical timeline, its own failure modes, its own history of close calls in testing. And we are going to end where the mission ends, in the waters of the Pacific Ocean, where recovery ships are already pre-positioned, waiting, watching the sky for a fireball that turns into a capsule hanging under parachutes. But before we get there, before we walk through the countdown minute by minute, we need to understand one more thing about what makes this particular reentry unique. Not just unique among modern missions, unique in the entire history of spaceflight. The 4 crew members of Artemis 2, Commander Reed Wiseman, pilot Victor Glover, mission specialist Christina Koch, and Canadian Space Agency astronaut Jeremy Hansen, will have spent approximately 10 days in space. They will have flown around the moon. They will have gone further from Earth than any human beings in 50 years. And then they will come home. The psychological dimension of those 20 minutes is something that does not appear in the engineering documents. It does not show up in the thermal analysis reports or the guidance and navigation algorithm reviews, but it is real. These 4 people will know, with a precision that very few human beings in history have ever experienced, exactly what is happening to their vehicle and exactly how close the margins are. They are not passengers. They are trained aerospace professionals who have studied the Orion reentry system in exhaustive detail. They know about the Artemis 1 heat shield findings. They know about the spallation. They know what the failure modes are. And they will be lying in their seats, unable to communicate with the ground, watching their instruments, feeling the G-forces build, watching the temperature readings on the heat shield, and waiting. Trusting the engineering, trusting the computer, trusting the tens of thousands of people who spent years building the system around them. 20 minutes. That is all it takes. 20 minutes to decide whether the most expensive, most complex, most symbolically important crewed mission in a generation succeeds or fails. The clock starts at atmospheric interface, the moment the capsule first encounters air dense enough to begin generating heat. It starts at approximately 122 kilometers above the surface of the Earth. It starts at a speed of 11 kilometers per second. It starts the moment the plasma ignites. And from that moment, nothing any human being on the surface of this planet does or says or thinks makes any difference at all. The countdown to those 20 minutes has already begun. Picture the darkness first, not the darkness of a room with the lights off, not the darkness of a moonless night in the countryside, far from city lights, where you can see the Milky Way stretched across the sky like a brush stroke. This is a different kind of darkness entirely. This is the darkness of deep space, The darkness that the Artemis 2 crew will have been living inside for 10 days. A darkness so complete, so absolute, so unbroken by any horizon or atmosphere or scattered light that the human brain struggles to process it as a natural thing. Stars do not twinkle in deep space, they burn. Fixed, hard, unblinking points of cold fire against a black that has no bottom and no edge. For 10 days that has been the view outside the windows of the Orion capsule. And then, in a matter of seconds, everything changes. The transition from deep space to atmospheric interface is not a gradual thing. There is no slow brightening, no gentle warming, no graceful descent through layers of thickening air, the way a commercial airplane descends through clouds on approach to an airport. The Orion capsule is traveling at 11 kilometers per second. At that speed, the entire sequence from first atmospheric contact to peak heating takes less than 4 minutes. The crew goes from floating in the silence of near vacuum to being encased in a column of fire hotter than the surface of the sun. And they go there faster than most people drive to work in the morning. This is what those 20 minutes actually feel like from inside the capsule. This is the human experience of the most dangerous re-entry in modern spaceflight. Let's begin at T-minus 30 minutes before atmospheric interface, because the re-entry sequence does not start when the plasma begins. It starts long before that, with a burn. Approximately 30 minutes before the capsule hits the atmosphere, while it is still in the vacuum of space, the crew performs what is called the entry interface preparation. The Orion capsule, like the Apollo command module before it, separates from its service module, the cylindrical structure that contains the propulsion system, the solar panels, and the life support consumables that have sustained the crew throughout the mission. The service module is jettisoned. It tumbles away and will itself re-enter the atmosphere and burn up, uncontrolled, somewhere over the ocean. The crew watches it go. It is, in a very literal sense, the last piece of infrastructure connecting them to the systems that have kept them alive in space. From this point forward, the only thing between them and the void is the Orion capsule itself. This moment, service module separation, is one of several points in the re-entry sequence where a failure would be immediately and unsurvivably fatal. If the service module does not separate cleanly, if it remains attached to the capsule at the wrong angle or with residual structural connection, the Orion cannot orient itself correctly for atmospheric entry. The heat shield must face forward, precisely aligned with the direction of travel, to within a tolerance of a few degrees. If that alignment is wrong when the plasma begins, the heat does not hit the heat shield. It hits the crew module. And the crew module is not designed to survive that. Separation occurs nominally. It has to. There is no contingency plan for a failed separation at this stage that ends with the crew coming home alive. With the service module gone, the capsule now has a very specific shape. A blunt-nosed cone, wider at the base than at the top, with the large circular heat shield forming the entire base. This shape is not accidental. It is not aesthetic. It is the product of decades of aerodynamic research into what geometry best manages the thermal and pressure loads of hypersonic atmospheric entry. The blunt shape creates a strong bow shock wave that stands off from the surface of the heat shield, keeping the hottest part of the plasma slightly separated from the material. A sharper shape would cut through that bow shock and allow the plasma to attach directly to the surface, which would be immediately fatal. The crew has been in their seats for hours at this point, suited up in their Orion Crew Survival System suits, Bright orange pressure suits designed to keep them alive in the event of a cabin depressurization during re-entry or water egress after splashdown. The suits are uncomfortable for extended wear. They are not designed for comfort. They are designed to buy time, to keep the body alive for long enough that rescue becomes possible. Inside the capsule, the 4 crew members are lying on their backs in contoured seats, facing upward, or more precisely, facing the direction the capsule is travelling, since in space there is no upward. The seats are angled and cushioned to distribute the G-forces that are coming across as wide an area of the body as possible. During peak deceleration, the pressure will be on their chests and backs, not on their spines, which is the direction the human body tolerates high G-forces best. The seats have been custom fitted to each crew member's body measurements. Every millimetre of that fit was deliberate. The guidance computer has already been given its final navigation solution, a precise calculation of the capsule's position, velocity, and trajectory, updated by star tracker readings taken in the hours before re-entry. The computer knows where it is, where it's going, and what it needs to do. It will make thousands of autonomous adjustments to maintain the correct entry angle throughout both atmospheric passes. The crew can monitor what the computer is doing. In extremis, a crew member could take manual control. But manual control of a hypersonic vehicle during re-entry is, in practice, not a realistic survival option. The adjustments required are too fast, too small, and too precisely integrated with the guidance algorithm to be replicated by human hands on a joystick. The computer flies this. The crew monitors. At T-5 minutes, the capsule begins to encounter the very outermost wisps of the atmosphere. At 122 kilometers altitude, the air is so thin that you could not breathe it, could not even detect it without sensitive instruments. But at 11 kilometers per second, even air this thin begins to matter. The first molecules of nitrogen and oxygen are being compressed in front of the heat shield. The temperature at the stagnation point, the very center of the heat shield, the point that takes the maximum thermal load, begins to rise. This is atmospheric interface. This is T0 on the re-entry clock. In the first 60 seconds after atmospheric interface, the thermal environment escalates with a speed that is genuinely difficult to communicate in ordinary language. 1 second after interface, the stagnation point temperature is a few hundred degrees. 10 seconds later, it is over 1,000. 30 seconds in, it has passed 2,000 degrees Celsius. By the time 60 seconds have elapsed since first atmospheric contact, the Orion heat shield stagnation point is experiencing temperatures approaching the upper limit of what AV coat was designed to handle, and the capsule is still travelling at nearly the speed it entered. The deceleration has begun. The crew can feel it. In the first minute it is relatively mild, perhaps 1 or 2 G. Uncomfortable after days in microgravity, in which the body has already begun losing bone density and muscle mass and recalibrating its fluid distribution, but manageable. The crew knows what is coming, and 1 or 2 G in this moment is almost a relief. It is the first confirmation that the atmosphere is doing its job, that the physics is working. But the plasma is already building. Approximately 90 seconds after atmospheric interface, the ionization around the capsule becomes dense enough to block radio frequency communications. This is the beginning of the blackout. It does not happen all at once. There is a brief period of degraded signal, broken transmissions, fragmentary words coming through the noise, and then silence. Total, complete, unbroken silence. In Houston at Mission Control, the flight controllers are watching their telemetry screens and listening to the communications loop. They know the blackout is coming. They have trained for it. They have sat through simulations of it dozens of times. The flight director has briefed the team. When comm goes dark, we continue nominal operations, we monitor the tracking data from the downrange radar stations, and we wait. But knowing a thing intellectually and experiencing it emotionally are not the same. The last communication from the crew before blackout is typically a brief, professional acknowledgement, a call-out of the entry parameters, a confirmation that the vehicle is behaving nominally, and then the loop goes quiet, and the 400 or so people in mission control and in the back rooms sit in front of their screens and watch data that is now 12 seconds old, the light speed delay from the vehicle's last position, and wait for the vehicle to come out the other side. For the crew inside the capsule, the blackout is a different kind of experience. They are not waiting for communications to be restored. They are busy. The first atmospheric pass is the most physically and operationally demanding phase of the entire mission. The G-forces are climbing toward their peak. The noise is extraordinary, and hypersonic airflow across the capsule structure, the crackling and groaning of thermal expansion in the spacecraft's frame, the hiss of the thrusters as the guidance computer makes continuous small adjustments to maintain the correct orientation. The crew cannot see outside. The windows are covered by an ablative boot that protects the glass from the plasma. But the instruments are live. Heat, shield, temperature, guidance state, G-force readout, trajectory deviation from nominal. The crew watches the numbers, watches for anything that tells them the computer is not managing the trajectory correctly, watches for heat shield temperatures outside the predicted envelope, watches for structural warnings, watches the G-meter climbing toward 3.5 G. The world presses in. Breathing requires effort. The chest wants to compress. Years of training have prepared the crew for this. Specific breathing techniques, muscle tensing patterns, the discipline to keep the eyes moving and the mind working despite the physical insult of deceleration. But this is not a simulation. The G-forces in the simulator feel the same. The consequences of failure do not. The heat shield is doing something remarkable and terrible on the outside of the capsule during this phase. The AV coat material is ablating, burning away in the controlled, designed fashion that engineers spent years calibrating. But it is not a clean, smooth process. The ablation happens in a structured way across the face of the heat shield, with the center experiencing the highest temperatures and the highest ablation rates, and the edges experiencing lower temperatures. The char layer that forms on the surface of the ablating material provides a degree of thermal protection to the fresh material beneath. But the char layer is also subject to the aerodynamic shear forces of the hypersonic airflow, forces that try to strip the char layer away before it has fully done its protective job. This is the mechanism that caused the unexpected spallation on Artemis 1. The char layer in certain regions of the heat shield broke apart under the combined thermal and mechanical stress. Pieces of charred AV coat detached. In most cases, the pieces were small, a few centimeters across. In some cases, they were larger. The largest piece that detached during the Artemis 1 re-entry was approximately the size of a human palm. Each detachment exposed fresh AV coat to the full thermal environment. Each exposure caused accelerated local ablation. The heat shield was consumed faster in those areas than the models had predicted. The margins were reduced, but they held. For Artemis 2, NASA made modifications to the AV coat layup and to the manufacturing process for the heat shield. They changed the way the material is bonded to the underlying structure in certain regions. They modified some of the density gradations in the ablative material. They ran new thermal and structural analyses using the Artemis 1 flight data as validation. They increased the conservatism in certain areas of the thermal model, but they cannot fully eliminate the uncertainty. Because the spallation mechanism is not perfectly understood, the models that predict when and where the char layer will fracture under combined thermal and mechanical stress are not perfect. They are very good. They are the best models that the ablative heat shield community has ever produced, but they are not perfect. And in a system where the margin between survival and catastrophe is measured in millimeters of remaining heat shield material, imperfect models carry weight. This is not a secret within the Artemis program. The engineers know it, NASA management knows it, the crew knows it. The heat shield team presented their analysis to the Artemis 2 crew during their re-entry training, including the Artemis 1 findings and the modifications made in response. The crew asked good questions. They always ask good questions. And then they accepted the risk, as astronauts do, because the alternative is not flying. And not flying means the mission never happens. And the mission matters. Approximately 4 minutes after atmospheric interface, the Orion capsule reaches peak heating. This is the worst moment on the thermal timeline. The stagnation point temperature is at its maximum. The ablation rate is at its highest. The G-forces are approaching their peak. The plasma sheath is at its thickest and most ionized. Communication is completely cut off, and this is the moment the capsule needs to execute the first of the 2 most critical guidance maneuvers in the re-entry sequence. It needs to begin setting up for the skip. The skip is not a passive event. The capsule does not simply bounce off the atmosphere the way a physical stone bounces off water. A stone bouncing across a lake surface is subject only to the geometry of the impact. The angle and velocity and surface tension determine the bounce. The Orion capsule is an aerodynamic body moving through a fluid medium. It generates lift. The amount of lift it generates depends on its orientation, specifically on its bank angle, the rotation of the capsule around its longitudinal axis. By adjusting the bank angle, the guidance computer can vary the direction and magnitude of the lift force, and by carefully managing the lift vector throughout the first atmospheric pass, the computer guides the capsule up and out of the atmosphere at precisely the right moment on precisely the right trajectory to set up the correct conditions for the second pass. If the computer manages the lift vector incorrectly during the first pass, if it maintains the wrong bank angle for too long, or transitions too early, or miscalculates the trajectory based on an atmosphere that is slightly denser or less dense than the model predicted, the skip trajectory changes. The capsule might re-enter the atmosphere at the wrong angle during the second pass, too steep, and the G-forces exceed the design limits. Too shallow, and the capsule doesn't decelerate enough, and the parachutes deploy into an airstream that is still moving too fast for them to survive. In the worst case, the skip trajectory is badly enough corrupted that the capsule exits the atmosphere entirely on a trajectory it cannot return from, with no remaining propulsion capability to correct it. That last scenario, skip failure leading to the capsule escaping back into space, is what engineers call an unrecoverable trajectory. There is no contingency. There is no backup. If the Orion capsule exits the atmosphere during the skip on a trajectory that takes it back into space, the crew dies. Not immediately. The life support system has consumables for several more days, but there is no rescue capability, no vehicle that could be launched and reach them in time. The crew would simply wait in an intact capsule until the oxygen ran out. This is the failure mode that nobody discusses in the press releases. It is the failure mode that lives inside the guidance algorithm, inside the thermal model uncertainties, inside the atmospheric density variations that can never be perfectly predicted. It is a failure mode with a very small probability. The guidance system has enormous robustness built into it, multiple layers of redundancy in the navigation solution, conservative margins on the trajectory corridor, but it is not a failure mode with zero probability, and the crew knows it. 5 minutes and 40 seconds after atmospheric interface, the peak G-forces begin to ease. The capsule has slowed from 11 kilometers per second to approximately 7 kilometers per second during the first atmospheric pass. It has shed nearly 40% of its entry kinetic energy in less than 6 minutes. The heat shield has given up a layer of itself to accomplish this. The plasma around the capsule is beginning to thin as the capsule's altitude increases because the computer has been managing the lift vector correctly, and the capsule is rising back toward the edge of the atmosphere. The G-forces drop below 2, then below 1. The crew is nearly weightless again. The noise from the hypersonic airflow fades. The thermal environment cools. The plasma sheath dissipates. For a few moments, perhaps 90 seconds, perhaps 2 minutes, depending on the exact trajectory, the Orion capsule is in the skip, above the atmosphere, in near vacuum, moving at approximately 7 kilometers per second. The plasma is gone. The heat shield, which has been on the front line of the most violent thermal environment in human spaceflight for 6 solid minutes, is getting its first respite. The crew, for the first time since atmospheric interface, can hear themselves think. And in Houston, something remarkable happens. The comm blackout ends. For a brief window, perhaps 60 to 90 seconds during the skip phase, the plasma around the capsule has dissipated enough that radio signals can get through again. The flight controllers, who have been sitting in disciplined silence for 6 minutes, suddenly have contact. The voice loop crackles, the telemetry data updates. For a few precious seconds, mission control can hear the crew, can see the spacecraft's state, can confirm that the first pass was nominal and that the skip trajectory looks correct. And then the capsule arcs back down, the atmosphere thickens again, the plasma rebuilds. And for the second time in 8 minutes, communication cuts out. The blackout returns. The second atmospheric pass is different from the first in almost every measurable way. The capsule is slower, 7 kilometers per second instead of 11. The peak temperatures are lower, approximately 1,600 degrees Celsius at the stagnation point instead of 2,760. The G-forces are gentler, peaking around 3G instead of nearly 4. The duration of the second pass before the capsule slows to parachute deployment speed is longer because the lower speed means lower deceleration, but the thermal environment is less extreme. In many ways, the second pass is the easier pass. But the heat shield going into the second pass is not the same heat shield that went into the first pass. It has already absorbed 6 minutes of peak thermal loading. It has already ablated. The char layer has already been stressed, potentially spalled in places, reformed in others. The AV coat that faces the second pass has less material remaining above it. The margins are smaller, and this is where the Artemis 1 data creates a specific concern that the re-entry engineers carry with them into every review. During Artemis 1, the spallation events that were detected, the char layer pieces that broke off, occurred predominantly during the transition between the first and second atmospheric passes. During the skip phase, as the thermal environment changed rapidly, the thermal stresses in the char layer were at their maximum. The material was hot from the first pass, cooling rapidly in the near vacuum of the skip, and then about to face the renewed thermal loading of the second pass. This rapid thermal cycling, heat, cool, heat again, placed specific mechanical stresses on the char layer that the pre-flight models had underestimated. For Artemis 2, the modified heat shield manufacturing process was designed specifically to address these transition phase stresses. The engineers believe they have solved it. The analysis supports that belief, but the only way to know for certain is to fly it. And when the Orion capsule carrying Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen dips back into the atmosphere for its second pass, slower, cooler, but with a heat shield that has already been through the worst fire in modern human spaceflight, that is when those thermal modifications will either prove themselves or not. The crew lies in their seats. The G-forces build again, more gently this time. The plasma reforms outside the windows they cannot see through. The noise returns, quieter, lower in pitch than the roar of the first pass, but still unmistakably the sound of a vehicle being decelerated by atmosphere at hypersonic speed. The computer manages the trajectory. The heat shield does its job. And somewhere around 9 minutes after atmospheric interface, roughly 9 minutes into the 20-minute countdown, the plasma begins to thin. Not because the capsule is exiting the atmosphere again. This time it is slowing down, genuinely slowing, dropping below the speeds at which dense plasma can sustain itself. The ionization envelope around the capsule dissipates from a raging inferno to a glow, to a shimmer, to nothing. The windows are clear again, and for the first time since atmospheric interface, the crew can see Earth. Not the Earth of orbit, the curve of the horizon, the blue marble from a distance. The Earth from 30 kilometers up, moving at supersonic but not hypersonic speed. The ocean below them, the sky above them transitioning from the black of near space to a deep blue, and then a lighter blue. The capsule is subsonic now, or close to it. The G-forces are falling away. The heat shield has done everything it was asked to do. There are 11 minutes left in the countdown, and the next thing that has to happen is something that has failed in testing, something with its own terrifying timeline. The parachute sequence. There is a particular kind of engineering failure that keeps parachute designers awake at night. It is not the catastrophic failure, the chute that simply does not open, the line that snaps, the canopy that shreds in the first second of deployment. Those failures are terrifying, but they are at least comprehensible. The physics is straightforward. The failure mode is obvious. You can look at the wreckage and understand what happened. The failure that haunts parachute engineers is the subtle one. The failure that happens not because something broke in a dramatic, visible way, but because a sequence of events that individually look nominal, each step performing within its design parameters, combine in a way that produces a result nobody predicted. A chute that opens correctly, inflates correctly, and then collapses. A line that holds the designed load and then fails at 80% of that load because of a specific combination of dynamic pressure and deployment angle that nobody thought to test. A timing sequence that works flawlessly in 1,000 simulations and then, in the one that matters, runs 2 seconds late. And 2 seconds, at this altitude and this speed, is the difference between a survivable landing and an unsurvivable one. This is the world that the Orion parachute system lives in, and understanding it requires going back, briefly, to a test program that most people following the Artemis missions have never heard of. A test program that, if you read the full reports rather than the press summaries, reveals just how difficult it is to design a parachute system capable of reliably bringing home a 5.5-ton crew capsule from the edge of space. But first, let us set the scene precisely. 9 minutes into the 20-minute re-entry countdown, the plasma has dissipated. The Orion capsule is at approximately 25 to 30 kilometers altitude, traveling at somewhere between Mach 0.8 and Mach 1.5, subsonic to low supersonic speed, depending on the exact trajectory of the second atmospheric pass. The heat shield has performed its function, the crew has survived the thermal environment and the G-forces of the skip re-entry. The guidance computer has successfully managed 2 atmospheric passes and brought the capsule to a point in space and at a speed where the parachute system can take over. From this moment forward, the capsule is essentially a falling object. There is no propulsion available. There are no wings. There is nothing that can alter the fundamental fact that 5,500 kilograms of spacecraft, containing 4 human beings, is falling toward the surface of the Pacific Ocean under the influence of gravity, and the only thing that can slow it down enough to make the landing survivable is a sequence of parachutes deploying in a specific order, at specific altitudes, at specific speeds. The sequence has to work, all of it, every step, in order, on time. And it has to work the first time, because there is no second chance. The Orion parachute system is, by the standards of spacecraft recovery systems, extraordinarily complex. It consists of 11 parachutes in total, divided into 3 categories, deployed in 3 distinct phases. The sequence begins at approximately 7,600 meters altitude, roughly the cruising altitude of a commercial helicopter, and ends at the ocean surface approximately 5 minutes later. The first phase is the forward bay cover jettison. The Orion capsule's parachutes are housed in a compartment at the top of the crew module, the forward bay, which is sealed by a protective cover during the high-speed portions of re-entry. Before any parachutes can deploy, this cover must be explosively jettisoned. Small pyrotechnic charges fire, the cover blows away, and the parachute compartment is open to the slipstream. This is a clean, fast event. It either works or it doesn't. If the cover fails to jettison, if the pyrotechnics misfire, if the cover sticks, nothing that comes after is possible. Assuming nominal cover jettison, 2 drogue parachutes deploy from the forward bay. The drogues are relatively small and about 7 meters in diameter each, and their purpose is not to slow the capsule significantly, but to stabilize it. At the speeds and altitudes where the drogues deploy, the capsule is still moving fast enough that an unstabilized descent, tumbling, oscillating, spinning, would create dynamic loads on the main parachutes when they deploy that could destroy them. The drogues straighten the capsule out, point it nose up, and hold it stable while the speed drops to a level where the main parachutes can safely deploy. The drogues stay deployed for approximately 2 minutes, 2 minutes during which the crew is falling, stable, at several hundred kilometers per hour, watching the altitude readout descend, waiting for the next event in the sequence. At approximately 2,700 meters altitude, the drogues are cut away. They are not retracted. They are simply released, cut free from the capsule by pyrotechnic line cutters, and they fall away. For a brief, deliberate moment, the capsule is in free fall with no parachutes deployed at all. This is by design. The timing between drogue release and pilot chute deployment is calculated to ensure that the drogues are fully clear of the capsule before the next phase begins, so that there is no risk of entanglement. Then 3 pilot parachutes deploy. The pilots are small, roughly 2.5 meters in diameter, and their job is to pull the main parachutes out of the forward bay. Each pilot chute is connected by a bridle to one of the 3 main parachutes. Packed in deployment bags in the forward bay, the pilots catch the airstream, generate drag, and the force of that drag pulls the deployment bags out, which then allows the main parachutes to extract and begin inflating. The 3 main parachutes are the heart of the system. Each one is approximately 35 meters in diameter when fully inflated, larger than most houses. Together, the 3 mains have a combined canopy area of nearly 3,000 square meters. They are the largest parachutes ever used on a crewed spacecraft. They are made of nylon, which at these temperatures and speeds and loads is required to simultaneously be lightweight, strong, flexible, and resistant to the specific failure modes that come with rapid high-load inflation in an unpredictable aerodynamic environment. The inflation of the main parachutes is a violent event. The capsule is still moving at well over 100 kilometers per hour when the mains begin to open. The force of inflation, the sudden resistance generated by 3 enormous canopies catching hundreds of cubic meters of air, creates what engineers call opening shock. It is a jolt, a hard, sudden deceleration that can generate brief G-forces of several G on the crew, superimposed on the much longer, gentler deceleration that follows as the fully inflated mains slow the capsule toward its terminal descent rate. The terminal descent rate under 3 main parachutes is approximately 8 meters per second. This is the speed at which the capsule will hit the water. 8 meters per second, roughly 29 kilometers per hour, is fast enough to feel extremely violent from inside the capsule, but slow enough that the impact attenuation built into the seats and the airbag system on the base of the crew module can absorb it without fatal injury to the crew. The seats are designed to stroke downward on impact, absorbing the deceleration over a slightly longer time period. The airbags, if deployed, cushion the base of the capsule as it contacts the water. This is the nominal sequence. Cover jettison, 2 drogues, 3 pilots, 3 mains, descent, splashdown, clean, sequential, each event triggering the next. Now let us talk about what can go wrong. The Orion parachute test program, which ran for over a decade before the Artemis 1 flight, included more than a dozen full-scale drop tests conducted over the Arizona desert using test articles dropped from high-altitude aircraft at various speeds and altitudes to simulate the conditions of an actual re-entry. The program was extensive. It was one of the most comprehensive spacecraft parachute test programs in the history of NASA, and it included a number of what the engineers euphemistically called anomalous results. In 2018, during a test designated as a main parachute stress test, one of the 3 main parachutes did not inflate correctly. The canopy opened but failed to pressurize uniformly, what engineers call a squid, or partial inflation, and collapsed shortly after deployment. The test was designed to demonstrate that the system could land safely with only 2 of the 3 main parachutes functioning. It was a deliberate one-shootout test, designed to qualify the system's failure margins. The test confirmed that 2 mains are sufficient for a survivable landing, but it also revealed specific deployment conditions, airspeed, altitude, capsule attitude, that produced higher than predicted dynamic loads during main chute inflation. In subsequent tests, engineers modified the reefing stages on the main parachutes. Reefing is a technique that limits the initial opening area of a parachute canopy, allowing it to inflate gradually rather than all at once, reducing the opening shock and the dynamic loads. The Orion main parachutes inflate in 2 reefing stages, first to about 12% of their full open area, then to about 67%, and finally to 100%. Each stage controlled by reefing line cutters that fire at timed intervals after deployment. The modifications to the reefing stages made the inflation process more gradual and more predictable, but reefing introduces its own complexity. Each reefing stage transition is controlled by small pyrotechnic cutters, the same kind of explosive devices used elsewhere in the parachute sequence. Each cutter must fire at the correct time. If a cutter fires early, the canopy inflates faster than designed, creating higher opening shock. If a cutter fires late, the canopy stays partially reefed for longer, descending faster than designed and potentially not fully inflating before ground contact. If a cutter fails entirely, if it does not fire at all, the canopy remains in its most restricted configuration, generating much less drag than a fully open main parachute. 3 main parachutes, 2 reefing stages each, 6 pyrotechnic cutters, all of which must fire at the correct time. On top of the line, cutters that release the drogues. On top of the pyrotechnics that jettison the forward bay cover. On top of the charges that deploy the pilot chutes. The Orion parachute system contains more than 100 pyrotechnic devices in total across all of its deployment mechanisms. Each one is a small explosive charge that must fire at a specific moment. Each one is a potential failure point. This is not a criticism of the design. Every spacecraft recovery system uses pyrotechnics extensively because pyrotechnics are fast, reliable, and require no mechanical actuation. A properly designed pyrotechnic device will fire within milliseconds of the electrical signal to ignite it every time, under almost any environmental conditions. The reliability of individual pyrotechnic devices is extremely high, measured in parts per million failure rates. But when you have 100 of them, the probability of at least one anomalous firing across the entire sequence, while still low, is not negligible. And the consequence of a pyrotechnic anomaly in the parachute sequence depends entirely on which device it is and what it does. Some failures are recoverable. If one of the 3 mains fails to fully inflate, the other 2 are sufficient. If the drogues deploy slightly late, the system is robust enough to handle the variation. But there are specific failure combinations, specific sequences of events that individually look close to nominal but combine badly, that would result in the capsule reaching the ocean surface faster than the impact attenuation system can handle. The survival limit for an Orion water landing is approximately 15 meters per second. Above that speed, the forces on the crew during impact exceed what the seats and suits can protect against. Not necessarily by a large margin. The difference between a survivable impact and a fatal one at these speeds is measured in meters per second, not tens of meters per second. But the boundary is real, and it is not far above the nominal terminal velocity of 8 meters per second. Under 2 main parachutes instead of 3, the terminal velocity is approximately 10 meters per second. Survivable, uncomfortable, within design margins. Under 1 main parachute, the terminal velocity is approximately 14 meters per second. At the boundary of survivability, the impact attenuation system would be pushed to or beyond its design limits. The crew might survive, they might not. Under no main parachutes, the capsule impacts the ocean at approximately 85 meters per second. This is not survivable by any mechanism available on the vehicle. The test program qualification requirement for the Orion parachute system is that it must demonstrate survivability With one main parachute failed, the two mains out scenario is not required to be survivable, though it is required to be analysed. NASA's position, supported by the test data, is that the probability of two or more main parachutes failing simultaneously is sufficiently low that it does not need to be designed against in the mission risk framework. This is a reasonable engineering judgment. It is the kind of judgment that every crewed spacecraft program makes, because if you required survivability against every possible failure combination, you would never fly. But it is worth sitting with for a moment, really sitting with, the fact that the survival of the Artemis 2 crew during the final 11 minutes of the mission depends on at least 2 of 3 parachutes deploying correctly through a sequence of more than 100 pyrotechnic events, none of which can be tested in the actual flight configuration until the moment they are needed. Every pyrotechnic device in the Orion parachute system was tested on the ground before installation. Every lot of pyrotechnic material was verified. The assembly and installation process was documented to aerospace quality standards. The completed parachute system was inspected. The software timing sequences for the deployment events were verified in simulation. But the devices were not fired. They cannot be fired in testing. A fired pyrotechnic device is consumed. You cannot test the actual flight hardware. You test representative hardware from the same manufacturing lot under the same conditions, and you accept that as qualification. The specific devices installed in the Artemis 2 capsule will fire for the first time over the Pacific Ocean, when they are needed, with 4 people's lives depending on them. This is the nature of pyrotechnic systems in spacecraft. It has always been this way. It will always be this way. And it works. The record of successful spacecraft recoveries using pyrotechnic deployment systems is long and reassuring, but the word works in this context means has always worked so far. It does not mean cannot fail. Now let us return to the crew falling through the final 11 minutes of the countdown inside a capsule that is now below 25,000 meters and slowing toward the drogue deployment altitude. The crew has been through the worst of it: the plasma, the blackout, the skip, the second pass. The physical violence of peak reentry is behind them. But the tension inside the capsule does not decrease as the parachute sequence approaches. If anything, it sharpens. Because this is the phase that in the crew's training produced the most complex emergency procedures. The high-speed thermal phase of re-entry is something you survive or you don't. There is relatively little the crew can do to influence the outcome once atmospheric interface begins. The parachute phase is different. There are things the crew can do. There are monitoring tasks, decision points, manual interventions available in certain failure scenarios. At 7,600 meters, the forward bay cover jettisons. The crew hears and feels the pyrotechnic charges fire, a sharp crack transmitted through the structure. The cover blows away. The forward bay is open. The drogues deploy. The crew feels the sudden jolt of the drogues catching the airstream, a brief, hard deceleration that pushes them into their seats. The capsule stabilizes. The oscillation from the high-speed descent dampens out. The descent rate, which was several hundred kilometers per hour, begins to slow. Through the windows, if any crew member looks up, the drogues are visible. 2 relatively small orange and white canopies streaming above the capsule, doing their quiet work of stabilization. Below them is the ocean, still far away but growing closer with every second. At 2,700 meters, the line cutters fire, the drogues release. The capsule, for one long second, is in free fall again, and then the pilots deploy, and an instant later the deployment bags are ripped out of the forward bay by the pilot chutes, and the 3 main parachutes begin to extract. The inflation of 3 35-meter parachutes takes several seconds. During those seconds, the crew is watching the parachute status indicators. The guidance computer is tracking the capsule's descent rate. Mission Control, which now has communication re-established since the plasma is gone, is receiving telemetry data and can see the parachute deployment status in real time. If a main chute fails to inflate, if the status indicator shows 2 mains instead of 3, the flight director has a decision to make. But it is not a decision that changes anything, because there is nothing Mission Control can do from the ground to fix a parachute that has failed to deploy over the ocean. The decision is whether to declare an emergency and accelerate the recovery fleet's response. The decision is how to communicate with the crew. The decision is how to prepare the recovery teams for the possibility of a harder landing. The crew's decision in a 2-main scenario is simpler. Execute the malfunction procedure, confirm the capsule is within survivable descent rate limits, and prepare for a harder than nominal water landing. Under normal circumstances, this does not happen. Under normal circumstances, all 3 mains open cleanly, inflate through their reefing stages, and the capsule descends at 8 meters per second under 3 enormous orange and white canopies, visible from the recovery ships as a bright cluster of color against the Pacific sky. From the recovery ships, which have been positioned in the anticipated splashdown zone for days, this is the moment everyone has been waiting for. The ships have tracking radar watching the re-entry trajectory. They have visual observers scanning the sky. They have been in constant communication with Mission Control. When the parachutes appear, when the radar tracks confirm the descent rate, when the visual observers report 3 mains deployed, the recovery operation shifts into its active phase. Swimmers are deployed. Rescue boats are launched. The ship maneuvers to the calculated splashdown point. Inside the capsule, the crew prepares for water impact. Seat harnesses are tightened. Suit integrity is confirmed. The landing and recovery system, the airbags, the post-landing ventilation, the beacon systems that will begin broadcasting the moment the capsule hits the water, is armed and ready. The ocean comes up. 8 meters per second. The capsule hits the water. The impact is violent. More violent than most people expect from what looks, from the outside, like a gentle parachute landing. 8 meters per second is nearly 30 kilometers per hour. The capsule is a 5.5-ton object. It hits the surface of the ocean and the water does not give way gracefully. It compresses, it resists, and the deceleration from impact speed to 0 takes place over a fraction of a second. The crew, despite the seat cushioning and the impact attenuation, is thrown hard into their harnesses. The structure of the capsule transmits the impact through every connection point, and then it is over. The capsule bobs on the surface of the Pacific. The parachutes collapse into the water around it, orange and white nylon covering the ocean surface like enormous, deflated balloons. The recovery beacon begins transmitting. The GPS location of the capsule appears on screens in Mission Control and on the recovery ships simultaneously. The swimmers are in the water. The boats are approaching. 19 minutes. And some seconds after atmospheric interface, 4 human beings who have been further from Earth than any humans in 50 years are floating on the surface of the Pacific Ocean, alive. But those 19 minutes contained something that we have not yet fully examined, something that exists not in the engineering of the heat shield or the parachutes, but in the specific, measurable, Historical record of what happens to human bodies during the precise physical experience the Artemis 2 crew will undergo. Because the skip re-entry does not just stress the vehicle, it stresses the people inside it. And the people inside Artemis 2 are not the same kind of people who flew the Apollo missions. The program has changed. The mission has changed. The crew has changed. And the question of whether the human body, specifically the specific bodies of these 4 specific human beings, can survive what those 20 minutes demand of it is a question that does not appear in the heat shield thermal models or the parachute deployment sequence documentation. It is a question that lives in the medical files, in the physiological studies, in the data from 10 days in microgravity, followed by peak G-loading, followed by water impact, in the specific individual vulnerabilities that every human being carries that no simulation can fully replicate, that no amount of training can entirely eliminate. There is a number that the Artemis 2 flight surgeons think about more than almost any other number in their planning documents. It is not a temperature. It is not a pressure. It is not a velocity or an altitude or a countdown timer. It is a percentage. Specifically, it is the percentage by which the volume of blood plasma in a human body decreases during the first 48 hours of exposure to microgravity. That number is approximately 15%. In the first 2 days after a person enters weightlessness, the body loses roughly 15% of its circulating blood plasma volume. Not blood cells, plasma, the fluid component. The body's fluid distribution system, which on Earth is organized entirely around the assumption that gravity is pulling fluid toward the feet and the lower body, suddenly finds itself in an environment where that assumption is no longer valid. Fluid that was being held in the legs and lower torso by the constant work of the cardiovascular system redistributes upward. The brain and upper body detect the increase in fluid pressure and interpret it incorrectly by Earth standards, but correctly by the logic of the new environment as a sign that the body is carrying too much fluid. It responds by telling the kidneys to excrete the excess. Urine output increases sharply in the first days of spaceflight. The body sheds fluid. The plasma volume drops. By day 10 of the Artemis 2 mission, the approximate duration of the lunar flyby trajectory, each of the 4 crew members will have a cardiovascular system that has been operating in microgravity long enough to have fully adapted to weightlessness. The heart, which on Earth beats against the constant resistance of pumping blood upward against gravity, has reduced its workload. The blood vessel walls, which on Earth maintain tone against the gravitational pressure column of the circulatory system, have relaxed. The orthostatic reflex, the automatic cardiovascular response that prevents fainting when you stand up quickly, has attenuated because it has not been needed. And then, 9 minutes into the 20-minute re-entry countdown, the deceleration begins. Gravity returns. Not the gentle, gradual return of an astronaut stepping off a plane after a week-long trip to the ISS. The sudden, hard, sustained return of up to 4 times normal gravity, pressing a cardiovascular system that has spent 10 days forgetting how to fight gravity back into a body that is simultaneously trying to remember how to manage the orthostatic response, redistribute fluid back into the lower body, and maintain adequate brain perfusion, all while the person it belongs to is also managing the cognitive and operational demands of monitoring a hypersonic vehicle during the most dangerous phase of the mission. This is what the flight surgeons call re-entry cardiovascular stress. And for the Artemis 2 crew, it is a more complex problem than it was for any ISS crew that has returned to Earth in recent years for one specific reason. The ISS crews return on a ballistic trajectory. The G-forces during a Soyuz re-entry, for example, build relatively quickly to their peak of around 4 EG and then decrease over the course of several minutes in a single continuous event. The total duration of significant G-loading above 2G is roughly 3 to 4 minutes. The body's cardiovascular response, though stressed, is dealing with a single sustained event. The Artemis 2 skip re-entry profile is different. The crew experiences significant G-loading during the first atmospheric pass, building toward 4G, sustained for several minutes. Then the G-forces drop nearly to zero during the skip phase. Then they build again during the second atmospheric pass, though to a lower peak. Then they drop again during the parachute phase. And then the water impact delivers a brief, sharp, impulsive load. This is not a single sustained event. It is an oscillating, interrupted sequence of high and low loading, interspersed with near weightlessness, followed by an impulsive shock. And the cardiovascular system, which has been managing without gravity for 10 days, has to adapt to this pattern in real time, with no warning and no warm-up. The concern is not that any single phase of this loading will exceed the structural limits of the human body. The concern is that the combination, the specific sequence of high G, low G, high G impact in a body that has been deconditioned by 10 days of microgravity creates a risk of cardiovascular decompensation that is greater than any individual phase would suggest. Cardiovascular decompensation during re-entry is not a theoretical concern. It has been documented, not in a fatal or near-fatal form. The record of crewed spacecraft returning from orbit does not include a case where a crew member suffered cardiac arrest during re-entry, but in forms that are measurable and concerning. Orthostatic hypotension, the drop in blood pressure that occurs when the cardiovascular system fails to respond quickly enough to the demand for increased perfusion as G-forces increase, has been recorded in returning astronauts. In most cases, it manifests as lightheadedness, tunnel vision, or grey out. In the worst documented cases, it has produced brief loss of consciousness. Loss of consciousness in a returning crew member during re-entry is not immediately fatal. The capsule is computer-guided. The other crew members are there. But it is a serious medical event in an environment where the crew member may be needed and where the physical and cognitive demands of the situation do not pause to accommodate someone who is unconscious. For the Artemis 2 mission specifically, the flight surgeons have implemented an aggressive countermeasures protocol. In the hours before re-entry, the crew performs fluid loading, drinking specific volumes of saline solution to temporarily increase their blood plasma volume before the cardiovascular stress of re-entry begins. They wear anti-G garments, compression suits, that squeeze the lower body to prevent blood pooling in the legs during the G-loading phases. They perform specific muscle tensing exercises during the high G phases that help push blood back toward the core and the brain. These countermeasures work. They have been validated in ISS return crews and in ground-based studies. They meaningfully reduce the cardiovascular risk of re-entry following microgravity exposure, but they do not eliminate it. And there is one member of the Artemis 2 crew whose specific physiological profile has drawn particular attention from the flight surgery team for reasons that are worth examining in some detail. Victor Glover, the pilot of Artemis 2, is the first black astronaut to fly on a long-duration spaceflight to the ISS. where he served as pilot on Crew Dragon Resilience in 2020 and 2021. He spent approximately 6 months on the ISS. His physiological data from that mission is extensive. NASA has detailed records of his cardiovascular response to microgravity, his fluid shifts, his muscle and bone density changes, and his recovery timeline following return to Earth. He is a known quantity to the flight surgeons in the best possible sense. His response to spaceflight has been studied, documented, and used to optimize his personal re-entry protocol for Artemis 2. But 6 months on the ISS, followed by recovery, followed by Artemis 2, means that Glover's body has been through the microgravity adaptation cycle twice. The question of whether repeated exposures to microgravity and the subsequent adaptation and readaptation cycles produce cumulative physiological effects that differ from what the pre-flight models predict is one that the aerospace medicine community does not yet have a definitive answer to. The data suggests that experienced astronauts recover from microgravity exposure more efficiently than first-time flyers, and that the cardiovascular response on subsequent flights tends to be more managed. But more managed is not the same as less risky, and the specific demands of a lunar return re-entry, which ISS crews do not face, introduce variables that Glover's prior flight data does not directly inform. Christina Koch, the mission specialist on Artemis 2, holds the record for the longest single spaceflight by a woman. She spent 328 consecutive days on the ISS from 2019 to 2020. Her long-duration physiological data is extraordinarily valuable to the flight surgeons, and her recovery from that mission was well documented and tracked closely. But 328 days in microgravity is also a physiological event with long-term consequences. Bone density losses of that magnitude take years to fully recover. Certain cardiovascular adaptations persist for months after return to Earth. The question of whether Koch's body, returning from a 10-day lunar flyby mission, is carrying any residual physiological signature from her record-breaking long-duration flight, and whether that residual signature interacts with the specific demands of the Artemis 2 re-entry in ways the models do not predict, is something the flight surgeons have modeled, tested, and continue to monitor. Jeremy Hansen, the Canadian Space Agency astronaut, is on his first spaceflight. This is his first experience of microgravity. His physiological response to the 10 days of weightlessness on Artemis 2 is, in some specific ways, the most uncertain of the 4 crew members, because there is no individual flight data on his specific body in microgravity. The pre-flight physiological screening has established his baseline. The ground-based centrifuge training, the parabolic flight experience, the isolation and confinement studies, all of these provide data. But the specific way that any individual human body adapts to actual spaceflight and then responds to the specific stresses of a skip re-entry contains individual variability that cannot be fully captured in ground-based testing. None of this means that any of these 4 crew members is expected to have a medical problem during re-entry. The flight surgeon's assessment, based on all available data, is that all 4 crew members are physiologically prepared for the demands of the Artemis 2 re-entry, and that the risk of a significant adverse medical event during those 20 minutes is low. But low is not zero. And understanding what the flight surgeons are watching for, what the specific physiological threats are during each phase of the 20 minutes, is important to understanding the full picture of what makes this re-entry so demanding. The first phase, Atmospheric interface through peak heating on the first pass is primarily a cardiovascular stress event. The G-forces building toward 4G in a deconditioned cardiovascular system is the primary concern. The countermeasures are active. The anti-G garments are doing their work. The crew is performing the muscle tensing protocols. The flight surgeons watching telemetry from the crew's biometric sensors, heart rate, blood oxygen saturation, respiration rate, are tracking every relevant parameter in real time. If a crew member's biometrics indicate a cardiovascular event during this phase, mission control is watching. But mission control cannot do anything. The comm is blacked out. The flight surgeon can watch the numbers change and be unable to speak to the crew. The crew members' crewmates, if they notice something wrong, can intervene physically, can check on their colleague, can administer a specific limited set of medical interventions that are available in the capsule. But the diagnosis of what is happening and the decision about what to do happens inside the capsule, without the flight surgeon's guidance, under 4G of deceleration, surrounded by plasma. This is, from a medical operations perspective, a genuinely harrowing situation. The flight surgeon community has worked extensively on training crew members in in-flight medical assessment and intervention. The Artemis II crew includes Reed Wiseman, the commander, who is a physician's son and has received extensive in-flight medical training. The crew, as a unit, has been trained in recognizing and responding to the specific medical scenarios that might arise during re-entry. They know what cardiovascular decompensation looks like. They know when to watch their crewmates and when to act. But knowing and doing under 4G of deceleration in a blackout are different things. The skip phase, the brief period of near weightlessness between the two atmospheric passes, introduces a specific physiological challenge that does not have a good analogue in existing spaceflight medicine data. The rapid transition from 4G to near 0G and back to 3G over a period of roughly 90 seconds is a cardiovascular stress pattern that has not been studied in detail in human subjects, because it has never occurred in crewed spaceflight before. The Apollo missions used ballistic re-entry, no skip, no G-force oscillation. ISS returns use ballistic re-entry. The only data on the physiological effects of skip re-entry in humans will be collected, for the first time, from the Artemis II crew. This is one of the explicit scientific objectives of the Artemis II mission. The crew will be wearing biometric monitoring equipment throughout re-entry specifically to collect physiological data on the skip re-entry profile. This data will be analyzed by the aerospace medicine community and used to improve the medical protocols and countermeasures for future Artemis missions, including the crewed lunar landing missions that come after. In this sense, the Artemis II crew are not just returning from the moon, they are generating the foundational data set on which the safety of every subsequent Artemis crew's re-entry will be based. The second atmospheric pass, as discussed in the context of the heat shield, is thermally less demanding than the first. But physiologically, it arrives when the crew's bodies have already been through the most intense phase of the re-entry. The cardiovascular system has already managed the first G-loading event. The muscles that have been fighting the G-forces have already consumed energy and generated lactic acid. The vestibular system, the inner ear balance apparatus, which has spent 10 days recalibrating for weightlessness, has been through 2 rounds of G-loading and 1 round of near weightlessness in the span of 15 minutes. The vestibular system deserves particular attention because it is one of the most consistently problematic physiological systems in returning astronauts and one of the least discussed in public coverage of spaceflight. The vestibular system is your body's primary mechanism for detecting orientation and acceleration. It works on Earth by detecting the direction and magnitude of the gravitational acceleration vector, the constant downward pull of gravity, and combining that information with signals from the muscles, joints, and visual system to maintain balance and orientation. In microgravity, the gravitational acceleration that the vestibular system evolved to detect is absent. The otolith organs, the gravity sensors in the inner ear, send confused, contradictory signals. Over the course of days in microgravity, the brain adapts. It learns to reweight the conflicting sensory inputs. It learns to interpret a specific pattern of sensory signals as, this is what normal feels like up here. And then re-entry begins, and everything changes again. During re-entry, the vestibular system is receiving sensory inputs that it has never encountered in exactly this configuration. The G-forces during the first atmospheric pass are in a direction that the vestibular system partly recognizes. They push in the chest-to-back direction, similar to the G-forces experienced in a high-performance aircraft maneuver, but the magnitude and duration are unusual, and they are occurring in a body that has just spent 10 days with effectively no vestibular input at all. The mismatch between what the vestibular system expects and what it receives produces, in many returning astronauts, significant motion sickness symptoms, nausea, disorientation, in some cases, vomiting. Vomiting in a spacesuit during re-entry is not simply unpleasant. It is a serious safety concern. The Orion crew's survival suits have provisions for managing this scenario. They are designed to allow the crew member to continue breathing safely even if vomiting occurs, but the scenario adds cognitive and physical load to a crew member who is already managing the demands of the re-entry and the G-forces and the monitoring requirements. The flight surgeons pre-medicate every Artemis crew member with anti-nausea medication before re-entry. The medication regimen used is aggressive by normal standards, a combination of drugs that target different mechanisms in the nausea response, chosen to provide maximum protection while minimizing side effects like drowsiness that could compromise cognitive performance. The crew takes their medication on a specific timeline before re-entry begins, calculated to ensure peak drug effectiveness during the most demanding phases. This works most of the time. But individual responses to anti-nausea medication vary, and the specific vestibular challenge of a skip re-entry, the oscillating G-force profile with its brief period of near weightlessness in the middle, is again something that has not been tested in this specific context before. There is one more physiological threat during those 20 minutes that is worth examining, and it is one that sits at the intersection of the vehicle's engineering and the crew's biology in a way that none of the other threats do. It is the threat from the heat. Inside the Orion crew module during re-entry, the cabin temperature rises. The heat shield is ablating on the outside of the vehicle, absorbing and carrying away enormous amounts of thermal energy. But the heat shield is not a perfect insulator. Some thermal energy is transmitted through the capsule structure into the cabin. The environmental control and life support system, the system that regulates the cabin temperature and the atmosphere, is working hard during re-entry to manage the cabin thermal environment. But during peak heating, particularly during the transition between the first and second atmospheric passes when the heat shield has already been maximally stressed, the cabin temperature can rise above the nominal comfort range. For a healthy person in a nominal physiological state, a cabin temperature somewhat above comfort is an annoyance, not a threat. But for a person who has already been through the cardiovascular stress of the first atmospheric pass, who is already working against G-forces, who is already managing the physiological demands of a body readapting to gravity. Elevated cabin temperature adds to the thermal load on the body's thermoregulation system. It demands additional cardiovascular output to manage core temperature. It compounds the other stresses rather than existing independently of them. This is, in the language of aerospace medicine, a compounding risk factor. No single one of the physiological threats during those 20 minutes, the cardiovascular stress of G-loading, the vestibular disruption, the potential cabin temperature elevation, the anti-G medication effects, the anti-nausea medication effects, the cumulative fatigue of 10 days in space is individually likely to cause a significant medical event in a healthy, well-prepared crew member. But they all occur simultaneously. They all act on the same body at the same time. And the combined effect of multiple moderate stresses in a deconditioned physiological system is not the same as the effect of any individual stressor acting alone. The flight surgeons know this. They have modeled it as well as the current state of aerospace medicine allows them to model it. They have built their countermeasures protocol to address the combination, not just the individual components. They are satisfied, based on all available data, that the 4 Artemis 2 crew members are prepared for what those 20 minutes will demand of their bodies. But they are also aware, because they are good scientists and honest physicians, that the Artemis 2 Reentry will generate data that does not currently exist. Data on what a skip re-entry actually does to a human body that has been in space for 10 days. Data that will either confirm their models or require them to be revised. Data that will be studied by the aerospace medicine community for years and used to protect the crews who come after. The 4 people in those seats are, in a very specific and measurable sense, making the future of deep space human medicine possible. They are the first data points in a data set that will eventually be large enough to give genuine confidence in the physiological safety of lunar return re-entry. But right now, in those 20 minutes, they are the only data points. And the thing about being the first data point in a new dataset is that you don't get to know in advance whether the model was right. You get to find out. The capsule is in the water now, in our imagining of those 20 minutes. It is bobbing on the surface of the Pacific. The recovery swimmers are approaching. Inside the capsule, 4 people who have just survived something that no human beings have survived in over 50 years are completing their post-landing checklist, verifying the cabin atmosphere, confirming suit integrity, marking the time. Mission Control is getting telemetry. The recovery ships are maneuvering. It looks, from the outside, like the hardest part is over. But there is one final phase of those 20 minutes and the 30 minutes that follow them that creates a specific and underappreciated danger that has nothing to do with plasma or parachutes or physiology. It has to do with the ocean, and whose systems had been powered down to almost nothing to conserve electricity, and a parachute deployment that worked when nobody was entirely certain it would. Jim Lovell, Jack Swigert, and Fred Hayes were alive. The mission that NASA had publicly called a successful failure was over, and then the recovery helicopter crew pulled them out of the water, and the flight surgeons who examined them in the hours that followed noted something that did not make the headlines and did not become part of the triumphant narrative of Apollo 13's survival. All 3 crew members were significantly hypothermic. Their core body temperatures had dropped measurably below normal during the final hours of the mission, when the command module had been powered down and the cabin temperature had fallen to near freezing levels. Hayes had developed a urinary tract infection during the mission that was already progressing toward kidney infection by the time he was recovered. The men who had just survived one of the greatest crises in spaceflight history were, by any clinical definition, not well. They recovered. All three of them recovered fully. But the Apollo 13 recovery is a useful reminder of something that tends to get lost in the drama of launch and re-entry and splashdown. The moment the capsule hits the water is not the end of the danger. It is the beginning of a new and distinct phase of danger, one with its own timeline, its own failure modes, and its own history of close calls that the official histories of spaceflight do not always surface. For the Artemis 2 crew, the water is where the final 11 minutes of physical danger live. 11 minutes that, in the nominal case, are routine and well managed, and end with 4 crew members being lifted into a recovery helicopter and transported to the USS San Diego, or whichever recovery vessel has been designated for the mission. 11 minutes that, in a non-nominal case, can transition from manageable to life-threatening, with a speed that the recovery teams plan for obsessively and hope never to see. Let us begin where we left off. The capsule has hit the water. The impact was hard, and it always is. 8 meters per second is not gentle. The crew has been through 4+ G of deceleration, a plasma blackout, a skip re-entry, a second atmospheric pass, and a parachute sequence. They have been awake for the better part of 20 hours. Their bodies are deconditioned from 10 days in microgravity. Their cardiovascular systems are in the process of readapting to gravity. Their vestibular systems are receiving sensory signals that conflict with 10 days of learned weightlessness. And they have just been hit hard by the Pacific Ocean. The first thing that happens after water contact is that the Orion capsule does something that surprises almost everyone who sees it for the first time in simulation or in the one existing splashdown video from Artemis 1. It rolls. The Orion capsule, floating on the ocean, is not stable with its heat shield down and its crew module up, the configuration it was in during descent, and the configuration that most people intuitively imagine it maintaining after splashdown. The capsule's center of mass and the geometry of its shape combine to produce a floating body that is more stable inverted, heat shield up, crew module down, crew members hanging upside down in their seats, than it is in the upright position. This is a known engineering characteristic. It is called the stable inverted, or stable 2 attitude in NASA documentation. The opposite, desired configuration, heat shield down, crew module up, is called stable 1. The Orion capsule is designed to float in either attitude and to be recoverable from either, but the probability that the capsule will end up in stable 2, inverted, after a Pacific Ocean splashdown is not negligible. Wave conditions, wind, the specific dynamics of the water impact, the state of the parachutes in the water around the capsule, all of these affect which stable attitude the capsule settles into. If the capsule is inverted, the crew is hanging upside down in their harnesses over the Pacific Ocean. Their suits are pressurized, they are physically intact, but they are inverted. The cabin atmosphere is being managed by systems that were designed for operation in both attitudes, and the recovery process is more complex. The Orion capsule has an uprighting system, a set of airbags that can be inflated around the crew module to flip the capsule from stable 2 back to stable 1. This system was tested extensively during the parachute and water landing test program. It works, but it requires time and it requires the capsule's power systems to be functioning, and it adds a step to the recovery timeline. That, in good sea conditions, is a manageable inconvenience and in bad sea conditions can become a serious complication. Sea conditions in the Pacific Ocean landing zone are not guaranteed to be good. The recovery planning for Artemis 2, like all crewed splashdown recoveries, includes weather contingencies. The splashdown trajectory can be adjusted, within limits, by modifying the re-entry flight path to target a different landing zone within the broad recovery area. Mission Control and the recovery fleet track weather continuously in the days before re-entry and make adjustments to the targeted landing point to avoid the worst sea states. But the Pacific Ocean is the Pacific Ocean. The window between the end of the second atmospheric pass and splashdown is roughly 11 minutes. The weather that exists when the capsule hits the water is the weather that the crew and the recovery teams deal with. The design sea state limit for Orion recovery operations, the maximum wave height and wind speed at which the recovery can be executed safely, is waves of up to approximately 5.5 meters, significant wave height, and winds up to 46 kilometers per hour. These are not gentle conditions. 5.5-meter waves are serious ocean conditions. They are the kind of conditions that make small boat operations extremely demanding. They are the kind of conditions in which a capsule bobbing on the surface and a recovery swimmer in the water and a small recovery boat all become parts of a dynamic, unpredictable system with multiple interaction points that each carry their own risk. The recovery team that will respond to the Artemis 2 splashdown is a specialized unit that has trained specifically for Orion recovery in a range of sea conditions. The swimmers are combat rescue officers from the United States Air Force, among the most highly trained water rescue professionals in the world. The recovery ships carry medical teams, equipment for extrication of crew members who cannot self-egress, and facilities for immediate medical assessment and stabilization. The helicopters and the ships and the swimmers operate as an integrated system with specific roles and specific timelines for each element. In the nominal case, the recovery timeline looks like this. The capsule splashes down. The recovery beacon begins transmitting immediately, giving the recovery ships GPS coordinates with meter-level accuracy. The ships are already positioned in the landing zone. They have been there for days. The first helicopter is in the air before splashdown, positioned to arrive at the capsule within minutes of water contact. The swimmers enter the water and attach a sea anchor to the capsule to reduce its drift, then stabilize a small recovery boat alongside the capsule. The forward hatch is opened from the outside, allowing fresh air into the cabin and beginning the crew extraction process. From splashdown to first crew member extracted, nominally approximately 30 to 45 minutes. This is where the physiology of the preceding 20 minutes becomes critical again. The Artemis 2 crew members, when the hatch opens, will be in various states of physiological compromise. They have been through the most demanding physical experience of the mission. They are deconditioned from 10 days of microgravity. Their cardiovascular systems are in the process of the difficult readaptation to gravity that begins the moment they hit the atmosphere and continues for hours or days afterward. In the nominal recovery scenario, the crew members are assisted out of the capsule by the recovery swimmers, transferred to the recovery boat or hoisted directly into the helicopter, and transported to the ship's medical facility for initial assessment. They are not expected to walk. The human body, after 10 days in microgravity and the cardiovascular stress of re-entry, does not walk reliably. The astronauts who stepped off the space shuttle after 2-week missions had difficulty walking without assistance. The Artemis 2 crew, after a lunar return re-entry, will be in a similar or more compromised state. The specific concern during crew extraction is orthostatic intolerance, the same cardiovascular decompensation risk that the flight surgeons were watching during re-entry, now manifesting in a different context. When a crew member transitions from the recline position in their seat to an upright position during egress, their cardiovascular system must rapidly increase blood pressure to maintain brain perfusion against the suddenly restored gravity vector. A cardiovascular system that has been through the stresses of the preceding 20 minutes may not respond quickly enough. The result can be sudden pre-syncope, the lightheadedness and tunnel vision that precede fainting, or full syncope, loss of consciousness, at exactly the moment when the crew member is being physically moved through a hatch and onto a boat or into a helicopter hoist. A crew member who loses consciousness during egress from a capsule floating on the Pacific Ocean is a crew member in serious danger. In a situation that the recovery team must manage without the ability to provide the kind of immediate medical intervention that would be available in a hospital. The recovery swimmers are trained in this scenario. They have practiced it. They know how to manage it. But managing an unconscious adult in a pressurized suit through a spacecraft hatch in ocean swells is not simple, and the time from loss of consciousness to medical stabilization is longer in this environment than it would be anywhere else. This is why the recovery timeline is so carefully designed and why the recovery team so carefully controls the pace of crew extraction. Nobody rushes. Nobody asks a crew member to do more than they can safely do. The process is slow, deliberate, and attentive to each crew member's individual condition in real time. But there is one scenario in the post-splashdown period that the recovery teams train for with particular intensity, because it has actually happened in the history of crewed spaceflight, and because its consequences, if not managed immediately and correctly, are fatal within minutes. Capsule flooding. The Orion crew module floats. It is designed to float, but it is also designed to be entered and exited through a hatch, and that hatch is at the top of the crew module when the capsule is in the stable 1 attitude. In rough sea conditions, opening the hatch while waves are breaking over the capsule creates a risk of water ingress. Water entering the crew module does not immediately sink the capsule. The capsule has sufficient buoyancy to remain afloat with a significant amount of water inside, but it does create a situation where the interior of the crew module is being flooded while the crew members are still strapped into their seats. The Liberty Bell 7 capsule, flown by Gus Grissom in 1961, sank in the Atlantic Ocean after splashdown when its hatch opened prematurely and the capsule flooded before the recovery helicopter could extract Grissom. Grissom himself survived only because he was out of the capsule before it sank, floating in his suit in the ocean while the helicopter struggled to rescue him. The capsule was lost for 38 years. Grissom nearly drowned. That was 1961, and spacecraft design has changed enormously since then. The Orion hatch opens from the outside, requiring deliberate action by the recovery swimmers, and it is not susceptible to the kind of accidental premature opening that cost Grissom his capsule. But the underlying physics of ocean recovery, the interaction between an open hatch and ocean swells, the risk of water ingress, the buoyancy margins of a capsule that was designed primarily to survive re-entry and only secondarily to survive extended ocean floating, those physics have not changed. The recovery team's protocol is designed specifically to manage the hatch opening timing relative to sea conditions. The swimmers assess the wave state before opening the hatch. They choose the timing of the hatch opening to coincide with a wave trough, maximizing the time available before the next crest arrives. They work quickly. They move efficiently. And in conditions where the sea state is at or near the limit of safe recovery operations, those timing decisions become critical in a way that requires the kind of calm, expert judgment that only comes from extensive training in genuinely bad water. The Artemis 2 recovery swimmers have that training. They have practiced hatch opening and crew extraction in sea conditions that exceed the nominal mission design requirements. They know what it looks like when a wave arrives faster than expected. They know how to manage it. But they also know, as all good professionals who work in hazardous environments know, that the ocean does not follow the protocol. Let us pull back now from the immediate physical details of the recovery and look at what those 20 minutes mean in the larger context of where the Artemis program is going and what it is trying to do. Artemis 2 is the second mission of the Artemis program. The first, Artemis 1, was uncrewed. The third, Artemis 3, is planned to land humans on the moon for the first time since 1972, specifically near the lunar South Pole, in a region of permanently shadowed craters where water ice has been confirmed to exist. The fourth and fifth missions will build on that foundation. The long-term vision extends to a sustained human presence on and around the moon, and eventually to the use of the moon as a proving ground for missions to Mars. All of those missions, every crewed mission beyond low Earth orbit in the foreseeable future, will face the same 20 minutes that Artemis 2 faces. Every crew that goes to the moon and comes home will face lunar return velocity reentry. Every one of them will face the skip reentry guidance challenge, the heat shield thermal margins, the parachute sequence, the cardiovascular stress of G-loading following deep space microgravity exposure, the ocean recovery in conditions that cannot be fully predicted. The 20 minutes that Artemis 2 faces are not unique to Artemis 2. They are the price of coming home from deep space, and humanity will be paying that price every time it sends people beyond Earth orbit. This is why the Artemis 2 re-entry matters so much beyond the immediate mission. The data that comes out of those 20 minutes, the heat shield ablation measurements, the guidance system performance data, the biometric records of 4 human bodies going through a skip re-entry for the first time, the parachute deployment telemetry, the recovery timeline in actual Pacific Ocean conditions, will form the foundational dataset for every re-entry risk assessment that follows. The decisions made about heat shield margins, about guidance algorithm conservatism, about medical countermeasure protocols, about recovery fleet positioning and training, all of those decisions will be made for missions that come after, based in significant part on what happens during Artemis 2's 20 minutes. In this sense, the 4 crew members of Artemis 2 are not just coming home. They are building the road that everyone who follows them will travel. The data their mission generates will directly influence the safety margins of the crews that land on the moon. The physiological data from their re-entry will shape the medical protocols used to protect the first woman and the next man who walk on the lunar surface. The heat shield performance data will be used to validate or modify the thermal protection systems on future Orion capsules. They are, in a specific and measurable way, taking on risk so that future crews face less of it. This is what astronauts have always done. It is what the Mercury astronauts did when they sat in capsules whose reliability was, by modern standards, genuinely terrifying. It is what the Apollo crews did when they accepted the calculated risks of a program that had never sent humans beyond Earth orbit and was learning as it went. It is what the Space Shuttle crews did, both before and after Challenger, both before and after Columbia. when they flew vehicles with known risk profiles that the program had assessed and accepted, and in some cases misjudged. The history of human spaceflight is a history of accepting risk in the presence of incomplete knowledge, managed by the best engineering and medicine and operations that the knowledge of the time could provide, in service of objectives that the people accepting the risk believed were worth it. The Artemis II crew believes their mission is worth it. They have said so in the careful, measured language that astronauts use when they talk about risk, which acknowledges the danger without dramatizing it and accepts the reality without pretending it away. Reed Wiseman, speaking about the mission in a pre-flight interview, described the program's approach to risk in terms that every astronaut who has ever flown would recognize: not the absence of fear, but the presence of preparation. Not certainty of success, but confidence in the people and the systems and the work. Victor Glover, asked about the heat shield concerns that followed the Artemis I analysis, said something that the engineers who built that heat shield have probably read more than once. He said that he trusts the people. Not the hardware in the abstract, the people who built the hardware, who analyzed the anomalies, who made the modifications, who checked their work and checked it again. The people who will be watching the telemetry during those 20 minutes with the focused, professional anxiety of men and women who have put years of their lives into making this work. Christina Koch, who has already spent more time in space than almost any human being alive, has spoken about the experience of deep space in terms that go beyond the technical. She has described the specific quality of the darkness beyond Earth orbit, the absence of the planet from the window, the unobstructed view of the universe, in ways that suggest she is not flying to the moon despite the risk, but in some sense because of what that risk represents. The willingness to go further, the refusal to let fear of the return define the limit of the journey. Jeremy Hansen, the first Canadian to fly beyond low Earth orbit, represents something that the Artemis program was specifically designed to represent: the expansion of who gets to go, who gets to make the journey, who takes on the risk and carries home the data and makes the road safer for those who follow. In those 20 minutes, they will all four be the same thing. 4 human beings in a machine, at the edge of what the machine can do and at the edge of what the human body can endure, coming home from a place that no human being has visited in half a century. Coming home through fire and plasma and gravity and ocean, through a sequence of events that each carry their own timeline and their own failure modes and their own history of close calls and near misses, and the quiet, unheralded engineering work that turned near misses into successes. The countdown to those 20 minutes has been running for years. It ran through the design reviews and the manufacturing inspections and the heat shield test campaigns and the parachute drop tests and the guidance algorithm validation studies and the flight surgeon medical reviews and the crew training simulations. It ran through the Artemis I mission and the heat shield analysis that followed. It ran through the modifications and the reanalyses and the acceptance reviews. It ran through the launch and the trans-lunar injection and the lunar flyby and the trans-Earth injection burn that points the capsule back toward home. It will run through the final approach, through the service module separation, through the atmospheric interface, through the plasma and the blackout and the skip and the second pass and the parachutes and the ocean and the recovery. And when it ends, when the hatch opens and the first crew members lifted out of the capsule and into the Pacific air and the recovery swimmer steadies them against the motion of the boat and someone on the recovery ship says the words that Mission Control has been waiting to hear. The countdown will not be over. It will simply reset for Artemis 3, for the crew that will actually land, For the 20 minutes they will face on the way home from the surface of the Moon with a data set that Artemis 2 made possible, with heat shield margins that Artemis 2 validated, with medical protocols that Artemis 2 refined, with a recovery team that Artemis 2 trained. The most dangerous 20 minutes in space are not a problem to be solved once and filed away. They are the permanent price of going further than Earth allows. They are the bill that comes due every time human beings decide that the distance to the horizon is not enough, that the next place worth going is the place beyond the place we can already reach, that the risk of the return is worth the wonder of the journey. 20 minutes, every time, for every crew, until we find a better way home, or until we stop going. And right now, in the spring of 2026, 4 people are preparing to pay that price on behalf of everyone who comes after them. The clock is running. Thank you for watching. If this video held your attention through the dark, the fire, and the ocean, share it with someone who asks why space still matters. The full countdown continues with our next video, where we examine the timeline of the Artemis 3 lunar landing itself, phase by phase, from powered descent initiation to the moment boots touch the surface of the Moon. Sleep well. The universe is patient. It will still be there when you wake up.